This is video number 4 for sections 11.4 and 11.5, solving nonlinear systems of equations. Okay, we've reached our final topic of the semester, and it's a good one to end on because it reviews something that we've done before and just extends on it a little bit. The topic that we have done before is what is called systems of linear equations. We did that a while back. Remember, those were the problems where we had two equations joined together in the same problem. And if we were asked to solve a system, what that meant was find an ordered pair, an XY pair, that works in both, that makes both equations true. We had three different methods that we used. We had kind of a visual graphing method, and then we had two algebra methods, elimination and substitution. The graphing method was pretty straightforward. You would take the first line and draw a graph, and you'd take the second line and draw a graph, and you'd figure out where those two lines intersect because we're looking for that one special ordered pair that works on both. Well, with two lines, this is pretty simple because two lines just intersect at one spot. We had some strange cases like parallel lines or overlapping lines, but for the most part, we had this situation just like in this picture. Now we're going to take this a little bit further, and we're going to talk about having a system of non-linear equations. Still two equations, but they will not both be lines. One of them might be a line, but certainly at least one of them will not be a line. Solving the system still means the same thing that it always has. It means look for ordered pairs that make both of the equations true. The thing is, though, this is going to get a lot more interesting now because when we did lines, pretty much there was one intersection point. But think about all the possibilities now. What if I had, say, a circle and then I had a parabola? Well, it's possible that the two things might only intersect once, like if the vertex of the parabola just kind of grazed the circle. On the other hand, it could be something like this, where the parabola intersects twice with the circle. Or what about something like this? That parabola, I think, just hit it 4 different times. You've got lots of possibilities now, and so that makes things a little bit more complicated. Because our time is short, we're going to solve all these problems the same exact way. We're going to start by graphing the system for the purpose of figuring out how many answers there are, and then we're going to use the method of substitution to actually find the solutions. So with that as a bit of background, let's go ahead and take a look at this first example problem here. We're being asked to solve this system of equations. We'll start out by drawing an accurate graph. We'll figure out how many solutions there are, and then we will use algebra to find them. The first thing we better do is figure out what in the world these things are. Hopefully, by this point, you're able to look at that first equation and go, okay, that's a circle. That's exactly what that is. It's a circle. It fits that pattern from the last lesson. It's actually a pretty simple circle because there's no h and k in here, which means the center is just at 0, 0. The radius, remember, is just the square root of this number here. This is the r squared. The square root of 4 would be 2. So this particular circle is centered at 0, 0, but with a radius of 2. So just go out 2 in each of the 4 directions, connect the dots, and you've got a circle. Okay, and then the second equation, what do I notice about that? I notice that I still have an x squared and a y squared. So that tells me it's one of these non-functions, one of these new shapes that we've learned. It's not a circle because circles cannot have different coefficients here at the front. That leaves me either with an ellipse or hyperbola, and the choice is easy. Plus is going to be ellipse, and minus is going to be hyperbola. So this guy is an ellipse. It's an ellipse that's not in the good format, though. So if I want to draw a picture of it, I need to get that 1 on the other side by dividing everybody by 64 and then simplifying. Let's see, 4 goes into 64 16 times, so I'll have a 16 here. And that, of course, means that 16 goes into 64 4 times. And then there's that 1 on the right. Once this is in the right format, I can jot down for myself the a and the b. A is the square root of 16. B is the square root of 2. Remember, the only ellipses we did are ones that are centered at 0, 0. The a tells me where the x-intercepts are, so 1, 2, 3, 4, and negative 4. And the b tells me the y-intercepts, up 2 there, positive 2, and negative 2. And now I can connect those dots. So here's my final graph showing the ellipse and the circle. And remember, I'm really just interested here in how many times they intersect. Well, I can see that they intersect once up top here and once down below. And in this problem, I can also tell what those 2 points are. I could write down the coordinates and be done, but we're going to follow that same method. We're just going to use the graph to figure out the number of solutions, but you are expected to know how to also show me the algebra to find the solutions. So let me go on to that next. I already said we're just going to focus on the method of substitution. Let's review for a minute how that worked. I'm going to use the original system here. This version here was great for the graphing, but it looks kind of messy for the algebra. So I'll just keep the equations as they originally were written there. The method of substitution is the one where you would pick one of the 4 letters, this x, this y, this x, this y, and isolate it, and then you would make a substitution into the other equation. Well, that's basically what I'm about to do with a slight twist. Since I notice that everybody is squared, instead of actually isolating an x or a y, I'll just isolate an x squared or a y squared, and that's going to be easier. I certainly should pick one of the ones from the top equation. These other 2 have coefficients. That'll be messier. So how about I go ahead and I pick the first x squared. So I'm going to take that x squared and I'm going to isolate it. That's pretty easy because all I have to do is subtract the y squared to the other side. And then I take that, I recopy my second equation, but when I get to the x squared part, I fill it in with my new name for x squared, which is 4 minus y squared. I've made a substitution. I've replaced the x squared with my new name 4 minus y squared. Copy the rest of it down the same. And then, just like we had earlier in the course, we now have an equation that just has one variable in it, which means I ought to be able to solve this pretty easily. It looks like it's going to be a quadratic equation. Let me go ahead and clean it up. 16 minus 4y squared. We'll copy down the rest. And then I've got some like terms. This is not going to be too bad of an equation to solve. It is quadratic, but there's only one letter y showing, so I can just use the square root method. So we'll subtract the 16, and then we will divide by the 12. Thankfully, this has worked out pretty nice. Go to square root, don't forget the plus or minus. And I end up here from this part with y equals plus or minus 2. Now that's not the end, right? We're looking for ordered pairs. So think back to the method of substitution. Once we figured out one of the letters, what we would do is we would go back to the substitution equation, which was this one. We would fill in the letter we had, in this case the y, so that we could solve for x. Now what I'm going to have to do is, since I found 2 different y's, I'm going to have to go ahead and plug each one into this to see the x that goes with it. So I'll start with the positive 2. I would take this, I would replace that y with a positive 2. This actually works out very easy because this side comes out to be 0. And when I square root, I can't really even have a plus or minus with a 0. I just get x equals 0. So that tells me that the y of positive 2 that we found goes with x equals 0. Now I'm wondering about the y of negative 2 that we found. What does that go with? Well, I just have to do the same thing. It turns out to be fairly boring because when you put that negative 2 in, the same exact thing happens. Negative 2 squared is still 4. You're still getting 0 over here. And of course, the square root of 0 is still 0. And so 0 goes with that y value as well. Here are my final two answers to this problem. Let's look back at the graph. Sure enough, here's 0, 2. Here's 0, negative 2. So it matches what our picture gave us. Again, I'm aware that we could see the answers right in the picture, but what you need to demonstrate is that you can do this algebra in terms of finding the solutions. I'll work some more examples in the next video.